The starting point for our travels to the outer edge of our universe is one of the driest places on Earth, the Atacama Desert. The European Southern Observatory, or ESO for short, is what makes this journey to the stars even possible. ESO is the motor that drives international astronomy research. Currently, it is supported by 16 member states. In northern Chile, ESO has 4 locations: Chajnantor, Paranal, La Silla, and soon Cerro Amazonas. There, in 2024, ESO will commence operation of the world's largest telescope. At the peak of the Cerro Paranal stand 4 mighty telescopes. This telescope array is the Very Large Telescope, or VLT for short. There are many reasons why the astronomers have chosen northern Chile to install their best celestial scouts.
This is one of the best places in the world for ground-based optical astronomy because of the very special geographical and atmospheric conditions we have here. When you look at the sky from the ground, you have to think like you're diving inside a bubble, which is our atmosphere, which is the air we breathe, the clouds, the wind, which is what allows life on Earth. But at the same time, it is an obstacle when we want to look at the sky. So we need places with very specific conditions. And the more sophisticated the machines, the more strict are those conditions to build giant telescopes. So basically what we look for is a place with a very low turbulence and a very clear atmosphere and very dry. Why dry? Because water vapors absorbs a lot, especially infrared radiation. And the turbulence, because the turbulence distorts the light, and therefore we have a poor image quality if the atmosphere is turbulent. So we have a very special configuration because we are just 12 kilometers away from the shore of the Pacific Ocean, but at the same time we are here at 2,600 meters of altitude. And we are above what we call the thermal inversion layer of the atmosphere, which determines the average altitude of the clouds cover. So this thing keeps all the moisture down at 1,100 meters above sea level. And above this layer, the atmosphere is very clear and is very calm. Then also we have these conditions very stable all over the year. This place is not very strongly affected by seasonal phenomena. So we have more or less the same conditions in the winter and in the summertime.
The ideal climatic conditions are an important factor for obtaining sharp images of the cosmos. In order to further enhance the telescope's vision, ESO engineers make use of some optical tricks. The foremost motto in telescope construction is, "The bigger, the better." The VLT's mirrors, with a diameter of 8.2 meters, are a good example. The 430-ton telescope platform moves with precision to set its sights on its celestial target. Four smaller, mobile auxiliary telescopes boost the VLT's optical power. This would make it possible to distinguish between the 2 headlights of a car standing on the surface of the Moon at a distance of 380,000 kilometers from Earth. In order to achieve this tremendous imaging quality, the light of the 4 large telescopes is combined. A virtual mirror with a diameter of 140 meters is created. If one adds the light of the 4 auxiliary telescopes, the size of the mirror grows to over 200 meters. The light is combined in underground tunnels to create a single focus. Due to the differing distances of the telescope to the common focal point, there is a minimal time delay between the beams of light. Mirror carriages compensate this delay with an accuracy of 1/1000th of a millimeter. Astronomers call the combination of telescopic light Interferometry. Constant measurements made by ESO engineers guarantee a consistently high-quality image. The interferometer of the VLT has captured the world's sharpest image of a star to date. The disk in the middle of the picture is the surface of the star itself. T. Leporus is surrounded by a shell of gas that is constantly being emitted by the giant star. A further trick called adaptive optics ensures even greater image sharpness. Thanks to a discharged laser beam that causes the existing sodium to glow at an altitude of 90 kilometers, an artificial lodestar is created. Wavefront sensors aimed at the lodestar measure the thermal distortions caused by the Earth's atmosphere. With the help of the measured data, a small mirror, positioned in the light path of the main mirror, is continuously distorted. This enables the correction of the atmospheric turbulences. The 23-ton heavy VLT primary mirror distorts itself under its own weight, causing the image to blur. This is where another trick called active optics comes into play. Plungers under the mirror push it back into its ideal shape. An image analyzer that continuously measures the surface of the mirror provides the data used to control the 150 actuators with nanometer precision. In recent decades, great progress has been made in researching our solar system. Space probes from Earth have visited planet after planet until in 2015, the dwarf planet Pluto was finally reached. But astronomers have even grander plans. Since the mid-90s, they have been tracking down planets in distant star systems, so-called exoplanets. The hunt for planets is the primary task of the SPHERE instrument that is mounted on a VLT mirror. Although only a small number of exoplanets have been detected so far, SPHERE has mastered this challenge well, allowing us a valuable look at the faint solar companions. The powerful planet finder blocks the light of the central star with the help of a disk. Otherwise, the star would simply outshine the planet, and it would remain invisible to us. The SPHERE instrument captures the polarized light of a star. The light of a star is always in a disordered state. When solar rays pass the surface of a planet, however, they are minimally directed and thus polarized. SPHERE captures this light, allowing a picture to be made of an exoplanet that is 300 light-years away. AU Microscopii is a young star surrounded by a dust disk, an important indicator for the creation of new planets. SPHERE is deployed in 2014 in the search for possible planets in this star system. In the process, the astronomers experience a real surprise. 5 wave-like arches can be seen moving away from the central star. The astronomers compare the images made by SPHERE with images from the Hubble Space Telescope made in previous years. The result of the long-term observation, the wave-like arches move extremely quickly and can even overcome the gravitational pull of the central star. Solar eruptions could be one explanation for this unusual phenomenon. Material from an orbiting planet is torn loose by the force of a solar eruption and ejected into space. In the immediate vicinity of the VLT, the VISTA survey telescope sets its focus on very large sections of the heavens.
VISTA's the first survey telescope called Paranal, and it nicely complements the existing very large telescopes, the 8-meter telescopes, because essentially doing surveys, it finds objects that they can study. So if you like, it finds the needles in a haystack, and then the VLTs will study in great detail the needles that have been found by VISTA and understand what they are and what's going on in, for example, the early universe. The thing that is special about VISTA is that it's got a large area. It's a 4-meter diameter mirror. It's got a very large field of view, about 1.5 degrees, and is also working in infrared. And that combination of those three properties make it the most powerful telescope in the world for doing infrared surveys.
With their telescopes, the astronomers observe not only the spectrum of light that is visible for our eyes, they also scan outer space from the gamma ray range to the radio wave range.
VISTA's a telescope with an infrared camera, and this allows us to look at the sky in a way that we can't see with an optical camera. So specifically, infrared cameras see preferentially cool objects, objects at a high redshift, or indeed objects that are hidden behind dust clouds.
The comparison between optical images, such as those made by the VLT, and the VISTA infrared images, clearly shows that astronomers are now able to gain a much more comprehensive insight when it comes to celestial bodies. A very different method of astronomical observation is the use of many very small telescopes. The Next Generation Transit Survey consists of 12 telescopes with a mirror of only 20 centimeters in diameter. The facility is designed to operate fully automatically and is able to continuously monitor the brightness of hundreds of thousands of stars in the southern sky. The mini telescopes look for planets that, seen from Earth, pass directly in front of their mother star. In the process, they block some of the star's light. This minimal fluctuation in brightness reveals the existence of a planet. With the help of the data gathered, the large ESO telescopes are then able to focus on the exoplanets that have been located by the mini telescopes. Are we able to ponder a thing that we can neither see, hear, smell, taste, nor feel? Astronomers have been facing this challenge for over 100 years. The center of our Milky Way. Here, an invisible secret lies hidden, and science fiction becomes reality. A supermassive black hole is sucking up everything that comes close to it. The mass of the black hole is 4 million times that of our Sun. Since the black hole allows no light to escape and is therefore invisible, it can only be detected indirectly. For more than 20 years now, the ESO telescopes have therefore been measuring the paths of objects orbiting around the black hole.
We have obtained the evidence for the black hole by looking at the motions of individual stars. And we have obtained orbits for around 30 stars. And these stars go around the black hole just like the planets go around the Sun. It was possible to follow the orbits of the stars by using adaptive optics on the Very Large Telescope, which allows us to look at the center of the Milky Way with a precision which is equivalent to seeing a coin at about 100-kilometer distance.
The center of the Milky Way contains yet another object, a cloud of gas. With a speed of 8 million kilometers per hour, it will soon be swallowed up by the black hole.
The cloud consists mainly of hydrogen gas which we see anyhow in the galactic center all over the place. This particular cloud weighs more or less 3 times the mass of Earth, so it's a rather small and tiny blob only, but it glows very brightly in the light of the stars which are surrounding the cloud. The black hole, imagine it sitting here, has a tremendous gravitational force, and the cloud, as it comes in, it will be elongated and stretched. It will become essentially like spaghetti. It will be elongated and falling into the black hole.
It borders on a paradox that here, of all places, in one of the least hospitable corners of the Earth, astronomers are searching for life on distant planets. But does not the Atacama Desert provide compelling proof that advanced life forms can flourish even under extreme conditions? In the barren mountainous regions of the Andes, wild animals struggle to survive. A condor has been tracking its prey since the early morning hours. The desert fox gets wind of a potential meal. And the vicuñas, finally, are waiting to be shorn for their valuable wool. A lizard emerges from a rare pool of water to warm itself in the desert sun. The reptile is always on its guard against predators. Pink flamingos add a touch of color. With their characteristic beaks, they filter plankton from the water. And with a bit of luck, they might also catch some small hermit crabs. For all the creatures here, water is essential. But it might take years for it to rain again. The first ESO facility was built in Chile in the 1960s. Since then, over 24 telescopes have been installed at the La Silla Observatory. For a long time, the Swedish ESO submillimeter telescope was the only telescope in the southern hemisphere capable of observing molecular clouds. The New Technology Telescope is the first large telescope to incorporate active and adaptive optics. When it was inaugurated in 1989, these were groundbreaking technologies in the field of celestial observation. TRAPPIST is dedicated to the study of comets in our solar system, as well as to the detection of exoplanets. The telescope is operated from a control room in Belgium. The name TRAPPIST was chosen because Trappist beer was the preferred drink of the Belgian astronomers. The Trappist monks hold the exclusive brewing rights for this royal barley drink. In 2017, there was cause for a toast as astronomers announced the discovery of a new solar system with a record number of 7 Earth-sized planets. The TRAPPIST telescope laid the foundation for this discovery. At least 3 of the rocky planets could be covered by oceans of water. Skywatching is not just about capturing images of distant worlds. If one wants to go into detail, one has to analyze the light of a star and study its composition. This approach, called spectrography, is one of the most powerful tools astronomers have at their disposal. In order to be able to read the light, it must be broken down into colors. Every chemical substance leaves an imprint of dark lines in the light of a star. These absorption lines are the fingerprints of the elements and, as such, form a unique pattern. Spectrography thus helps us to gain an in-depth understanding of matter in outer space. The HARPS spectrograph is attached to the 3.6-meter ESO telescope. The instrument holds the record for the detection of exoplanets.
HARPS is absolutely a fascinating spectrograph with an extreme sensitivity. It's a vacuum spectrometer with extreme stability on the long term. So at the present time, most of the low mass planets have been discovered by this instrument at La Silla in Chile.
HARPS can measure velocities of less than 3.5 kilometers per hour. That is equivalent to the speed of a very leisurely walk on Earth.
Most of the planets discovered today have been discovered just by the wobble of the velocity of a star, because you have the gravitational influence of the planet turning around. And evidently, less massive is the planet, more is difficult to detect it. If the mass of the planet is large enough, like the mass of Jupiter or more massive, in fact, we have almost no choice. It should be a big ball of gas, hydrogen, of helium. When we have planets in the range of few Earth mass, it's much more difficult. The nature of this object could be quite different. It could be rocky planets, it could be a big piece of ice, but if this planet migrate close to the star, we can have an ocean at the surface, or it could be some kind of evaporate gaseous giant. So it's much more difficult to be sure of the nature of this kind of low mass object.
In 1995, Professor Mayur and his team discovered the first exoplanet revolving around a sun-like star. Since then, the search for life on other planets has been the holy grail of astronomy. Until now, however, it has never been possible to provide evidence for life forms on an exoplanet. The planet must be located within the habitable zone. This zone is the narrow range in which a planet must be located in relation to its central star in order for water to exist permanently in liquid form. If it is too close to the sun, it will be bombarded by deadly X-rays. If it is too far from its mother star, it will become a frozen desert of ice. Optical telescopes cannot depict the surface of a planet, but radio telescopes listen for signals from alien civilizations, in the hopes that the aliens are just as curious as we are. We could get lucky and find signs of a highly developed civilization, perhaps a ring world, an artificial structure built around a star. But the chances for this are likely to be rather small. So far, there are more than 3,500 known exoplanets, with new ones being added every day. It won't be long before we will be able to say, we are not alone in the universe. Could it be that our cosmic neighbors are not even that far away from us? Measurement data indicates that the nearest star to Earth, Proxima Centauri, is orbited by a habitable planet. But since red dwarfs like Proxima Centauri are changeable stars, they can mimic the appearance of a planet. In order to find out more, a global observation campaign has been launched.
I, together with my colleagues, are representing the Pale Red Dot Collaboration, a project that joins 31 scientists of 8 countries around the world to study and search for exoplanets around our closest neighbor, Proxima Centauri. The star revealed a signal which was significant but was not unique. And we were not sure then if that signal was due to magnetic activity. That's why we started the Pale Red Dot campaign. It has finished, and it finished successfully.
What we are doing here is basically measuring the motion of this star over a few orbital periods, over a few periods of this signal that we thought it was in the data. For this, we are using the HARPS spectrograph, and also we are looking at the star with photometric telescopes that basically tell us if the star is flaring, if there is activity, if the star is rotating, or is something that could be causing this signal that we saw in the previous data, and we are trying to confirm now. We conclude that Proxima Centauri is orbited by a planet at an 11.2 days period. That gives us, we can estimate that the mass of the planet is around 1.3 Earth masses, and that's basically the information that we have. From that, we can use Kepler's law to infer the distance between the planet and the star, and for example, its temperature. And this is what my colleague Ansgar will tell you about.
Knowing the temperature of the star, this means that the temperature on the planet is very similar to the one on Earth, assuming the planet also has an atmosphere. We also know that the mass of the planet is 1.3 Earth masses. That's the minimum mass, but it's quite unlikely that it's a lot higher than this. From this, and simulations and other observations from other missions, we can infer that this planet actually has a surface. And if it has a surface, if it has an atmosphere, and if it has water, it is quite likely that it is very similar to Earth. Now, does this planet have an atmosphere? Does it have water? We don't know. But it is not excluded. Different models of planet formation and planet evolution tell us that there are scenarios that can end up with a planet with an atmosphere and with water. And so it is not unlikely that this planet is quite similar to Earth. The spectacular finding about this, of course, is that this system is so close to our Earth and solar system. And in the next generations, we will learn a lot about the system because Proxima b is our neighbor.
The Breakthrough Initiatives have established a research program called Starshot. The goal of the project is to send a space probe to our neighboring star. On the board of directors are the astrophysicist Stephen Hawking, the founder of the Breakthrough Initiatives and internet billionaire Yuri Milner, as well as Facebook founder Mark Zuckerberg. With the Breakthrough Initiatives, ESO has signed an agreement to finance the modification of the VLT instruments. This will enable a more precise search of Proxima Centauri for habitable planets and a more exact calculation of the flight paths for space probes. The Starshot concept revolves around the installation of laser cannons on Earth, which are used to power a light sail spacecraft that is deployed in outer space. The laser cannons combine their light output into a 100 gigawatt laser beam. The highly reflective sail is irradiated over a distance of 2 million kilometers for a period of 10 minutes, until a speed of 1/5 the speed of light is reached. Once the spacecraft reaches Proxima Centauri, after a 20-year journey, it slows down with the help of the star's gravitational force. This allows a flyby of the planet Proxima b, while the probe collects atmospheric data and images of the planet. The spacecraft then sends the entire data package back to Earth. As the laser signal is transmitted through space at the speed of light, the data package arrives at the receiving station after only 4.3 years. And the mysteries of Proxima b can be solved. Another night of observation begins in La Silla. For the astronomers in the control room, the work routine begins. Soon, however, an event in outer space will capture the attention of the observation team. At the end of its lifespan, a massive star collapses. This triggers an enormous gamma-ray burst. Particles and hard gamma radiation are emitted from the dying star. Such bright bursts of gamma rays are also caused by neutron stars or supernovae colliding with a black hole. NASA's SWIFT satellite detects a gamma ray burst in space and transmits the position to the ground-based telescopes on Earth. The time of peace and quiet at La Silla is over. Without human intervention, 3 robotic telescopes begin their observation program within minutes. Gamma ray bursts are so bright that they can outshine an entire galaxy. And yet the observation must take place immediately, as the afterglow lasts only a few hours. In the Paranal Observatory as well, the gamma ray bursts are being monitored closely. The core of a planetary nebula consists of 2 white dwarfs. The spiral orbits get closer and closer until the stars merge and a supernova comes into being. The gamma ray burst puts the VLT into rapid response mode. On the control panel, the telescope operators ensure that the VLT can be safely moved. The telescope then carries out the observation fully automatically. This allows the astronomers to observe the gamma ray bursts within minutes of their discovery. With such short-lived events, the length of time that passes determines whether one can gather high-quality data or no data at all. The Chaknantura High Plateau, with an elevation of 5,000 meters above sea level, is the highest ESO telescope site. ALMA, the Atacama Large Millimeter Submillimeter Array, allows the observation of wavelengths of around 1 millimeter, which lie between the infrared and radio wave ranges. The extreme elevation opens a window onto the universe that until now had not been visible from lower regions, where water vapor literally swallows up the millimeter wavelengths. The Operation Support Facility, or OSF for short, is where the antenna components are assembled and serviced. ALMA is the result of international cooperation between the European ESO partners, the United States and Canada, as well as Japan, South Korea, and Taiwan. The radio telescopes must be solidly built to withstand temperatures of between -20 and +20 degrees Celsius, fierce high-altitude winds, and intense solar radiation. The large, metallic, reflective dishes are up to 12 meters in size and are adjusted so precisely that their maximum imprecision is less than 25 micrometers. That is thinner than a sheet of paper. It took over 10 years for the ALMA project to be realized. The official commissioning of the ALMA facility in March 2013 gets an enthusiastic welcome from space.
Greetings from the International Space Station. I'm Expedition 34 Flight Engineer Tom Marshburn with my crewmate, Chris Hadfield of the Canadian Space Agency. As we look down upon the magnificent Atacama Desert high in the Chilean Andes, we can see the results of an immense effort by the nations of the world to study the universe in new ways. Today, a giant telescope called ALMA, the Atacama Large Millimeter Submillimeter Array, is being inaugurated. Comprised of 66 large radio dishes spread across miles of high-altitude desert, ALMA is opening a new frontier. Millimeter and submillimeter wavelength light from space carries precious information about the formation and evolution of galaxies, stars, planetary systems, and even the molecular precursors of life.
Together with the National Science Foundation, Carl G. Jansky Very Large Array, NASA's Hubble Telescope, the future James Webb Space Telescope, ALMA will enable the exploration of the universe with unprecedented power. We congratulate the scientific communities of North America and Europe and East Asia on today's achievement. All the very best to you, and enjoy your new discoveries.
The ALMA array did not take long to produce the first spectacular discoveries. Using millimeter radiation, ALMA makes celestial bodies visible that have a temperature of only a few degrees above absolute zero, which is minus 273 degrees Celsius. Among the first images captured by ALMA are the gas clouds in the radio galaxy Centaurus A. For the first time, the cool gas clouds of the neighboring galaxy become visible. The 66 antennas are spread out across 16 kilometers on the Chaknon Tor Plateau. The result is an enormous radio telescope, with which a golf ball could be recognized at a distance of 15 kilometers. At a breathtaking altitude of 5,000 meters above sea level, the ALMA operation site is the highest high-tech building on our planet. It houses a supercomputer called the correlator that processes the signals of all the individual antennas. At 5,000 meters, the air is so thin that twice the normal airflow is needed to cool the hard drives. The world's highest elevation supercomputer combines 134 million processors and manages 17 quadrillion calculations per second. The low air pressure also makes it impossible to use conventional rotating hard drives. In addition, the correlator must also be able to withstand the earthquakes that frequently occur in Chile. One focus of ALMA's observation activities is on protoplanetary disks. This is a region around a star where new planets are formed. The picture shows such a disk around the young star HL Tauri. The newly forming planets tear apart the gas disk surrounding the host star. ALMA makes this important evolutionary step in the creation of planets visible. Within the protoplanetary disks, lumps of rock form out of dust particles, building material for future asteroids, comets, and planets. Another of ALMA's capabilities is the detection of molecular structures. Sugar molecules have formed around the Sun-like double star Iris 16293-2422. Here, the building blocks of life are present in the right place and at the right time, allowing them to become part of the planets forming around the stars. In the disk surrounding the star TW Hydrae, ALMA detects methyl alcohol molecules, another basis for future life forms that has been discovered in a protoplanetary disk. how do you actually transport the 100-ton ALMA antennas from the OSF base camp at 2,900 meters up to the Chachnan Tor high plateau at an elevation of 5,000 meters? Two powerhouses named Otto and Lor go into action. The ALMA transport vehicles are burly wonders of engineering, 20 meters long, 10 meters wide, and 6 meters high. The heavy-duty transporters have 28 wheels, each functioning as a pair, which can rotate independently of one another in any direction. A 28-kilometer trip is required to reach the Chachnan Tor plateau. At a maximum speed of 12 kilometers per hour, an elevation difference of around 2,100 meters has to be overcome. The monster truck is equipped with a suspension system that can compensate at any time for the unevenness of the dirt roads. With increasing altitude, the power of the 700 horsepower engine drops dramatically. The reason for this is the low oxygen content in the air. After nearly 3 hours, the plateau is reached. A remote control is used to externally control the heavy-duty transporter until the anchor place is reached. Carefully, with millimeter precision, the sensitive mirror is set down on the base plate. The transport team is rewarded for their effort with a beautiful dusk. There is a striking similarity between the surface of Mars and the terrain of the Atacama Desert. This natural simulation terrain is ideal for the testing of Mars rover vehicles. The Atacama Desert is nearly as dry as the Red Planet. On average, less than 2 liters of rain per square meter fall in the high Andes per year. These are typical desert conditions. Ultraviolet radiation levels are twice as high as at normal elevation. During the day, the thermometer reaches 30 degrees Celsius, while at night, it drops to a frigid -15 degrees. Due to the arid climate, only a few species can survive here, such as the fescue bush, which is able to cover the ground during the dry season as well. The giant cacti that can grow up to 9 meters in height are also able to survive, despite the scarcity of water. Desert grass is another extremely robust plant species that thrives in the high desert climate. But then, something completely extraordinary happens. Overnight, the desert explodes in a sea of color. For several weeks, the plants are in full bloom, conquering what had until then been an extremely inhospitable corner of the globe. If such magnificent flora can bloom with so little water in the barren wasteland of the Atacama Desert, couldn't this example encourage us humans to one day turn the desert planet of Mars into a habitable blue world? The 3,000-meter-high summit of the Cerro Amazonas is the future home of the European Extremely Large Telescope, or EELT for short. The leveling of the mountain is the first milestone for the world's largest telescope, which will be able to make observations in both optical and infrared ranges. The first construction phase of the EELT began in 2014. Construction costs alone amount to approximately 1 billion euros. The countdown is running. Blast experts are laying the foundation for a new era in the history of astronomy.
Diez, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Today's telescope domes are dwarfed by the EELT. The rotating 85-meter dome alone weighs 5,000 tons. And the list of superlatives goes on. It collects 13 times more light than any other optical telescope in use today. This is made possible by the gigantic 39-meter diameter primary mirror. The light that is captured then passes across 5 mirrors, thus enabling a relatively compact design. The new telescope design includes a system of adaptive optics that allows for the tracking of 4 lodestars at the same time. The primary mirror is not made of one piece, but is constructed out of 798 hexagonal mirror segments. Each segment has a diameter of 1.4 meters and is only 50 millimeters thick. In an assembly facility at ESO in Munich-Garching, engineers test the interplay of mirror segments on a prototype. After it goes into operation in the year 2024, the EELT will begin to tackle some of the greatest scientific challenges of our time. Perhaps it will air the secrets of dark matter and of dark energy. The EELT will capture images of comets and planets within young star systems and will analyze its atmospheres, always in search of traces of life. The big eye on the skies will lift the veil left by remnants of supernovae, thereby contributing to a better understanding of the colossal star explosions. The telescope will also make fundamental contributions to cosmology by providing us with insights into the intricate structures of galaxies. It will gather important data about the expansion of the universe, its gravitational forces, as well as the formation of new stars and black holes. At the end of our cosmic journey, one thing is certain. We should always expect the unexpected. Out in the universe, surprising discoveries await us that cannot be foreseen from today's perspective.